Okay. Can you guys hear me for this mic? Okay, so I'm going to be talking about TensorFlow and how to do deep learning with Python. And so just to give you an introduction to myself. My name's Ian Lewis. I'm a developer advocate at Google. I work on the Google Cloud Platform team. I'm based in Tokyo, Japan, so I spend a lot of time in APAC, traveling to Taiwan and Korea and places like that. I'm also on Twitter, so if you guys have any questions or anything like that after the talk. Oh, you want to use this mic? Okay.
But this mic also.
Oh, you want to use both of them? Okay. Got it. So I need to use this one apparently. So I'm also on Twitter, so if you have any questions or anything like that after the talk, then you can come in or you can send me a message. I'd be happy to talk with you then. I'm also a organizer for PyCon JP in Japan. So I think that most of the tickets are pretty much sold out this year, but I hope to see most of you guys at PyCon JP next year. Submit lots of talks. I'm also fairly active in the Go communities as well as the Docker and containers related communities. So before talking about TensorFlow, I want to go back and talk a little bit about what deep learning is and give an introduction to a little bit of the technical parts of deep learning. So deep learning is essentially a type of is a specific type of machine learning. Specifically, we're talking about neural networks. And neural networks are typically made of these interconnected nodes or parts. And those are organized into layers. And so what we would have is an input layer here. Like this blue, these different colors represent different layers. So we have this blue input layer. Then we'll have a hidden layer. This does some operations on the input data. And then we get an output in an output layer. And we could have many input or many hidden layers in between here. This is just an example with one single layer. So neural networks are very good at a couple of different types of problems. One of the types of problems that it's very good at is classification. So that's basically deciding which bucket an input fits in. So like you might have, categories or things like that. Or another is a type called regression, which allows you to kind of take the points and kind of figure out a more linear value or on a kind of a scale values. But I'm going to be talking mostly about the classification problems. So a typical neural network problem, if the Wi-Fi is cooperative, we can look at this demo. But essentially what you'll have is like you have different types of categorized or data that comes into your model, and you want to be able to categorize whether it's blue or orange or however many categories you have. So here's a simple example. If we look over here, we have some blue and orange data. This blue and orange data might represent, say, maybe children for the orange and blue for the adults. And this might be their height, and this might be their width. The x and y values might be the height and width, or height and weight, sorry. So the we want to be able to categorize any new input data based like height and width as either being a child or an adult. And this is a very simple problem. You can basically just draw a line between these two, and it will correctly categorize the data. So here, anything on this side of the line is blue, which means it's an adult, and anything on the other side is a child, right? So this is a very easy problem. But what if we have more complicated problems? So say this one, it's kind of a spiral. How do we create an algorithm that can tell which category, blue or orange, to pick? Well, in order to do this, we have to have a much more complicated kind of network. So here I'm going to kind of create a more complicated network. So you have to give it like more complicated inputs and have many more of these kind of interconnected layers in order to actually create something that will be able to correctly categorize the data. So if I continue training this, it'll actually do a little bit better job, but you kind of get the idea. To actually do something that's useful, we have to have something like a neural network that we can train to be able to categorize the data. So what is a neural network in reality? So a neural network essentially is a bunch of operations that you do on some values or some data, and that data is typically represented as tensors. So many people are maybe not familiar with tensors, but maybe you're familiar with matrices that you learned in your high school math class. And so tensors are very similar to matrices in that you can multiply and add them together and things like that. But what we essentially will do is say take a picture, like a cat picture, and then we change that into a tensor or like a matrix. And then we do things like matrix multiplication and matrix addition several times in many different layers, in order to get an output that says like this is a cat, or this is a dog, or this is a person. So each of these interconnected layers are detecting some sort of feature of the image, but essentially what you're doing is just doing these types of matrix multiplications and additions and operations on the input data. So I talked about tensors and those that they're similar to matrices, but how are they different? So you can think of in programming, if you're all familiar with things like arrays, then you'll know that something like a regular array or a vector could be represented as a regular single-dimensional array, and something like a matrix could be represented as like a two-dimensional or a three-dimensional array. But a tensor is a much more generic type. So a vector is a type of tensor, or a matrix is a type of tensor. But a tensor essentially has any number of dimensions. It can have 2 or 3 or 100 or 1,000,000 dimensions. But you can still do the same sort of operations on a tensor as you could for matrices, like these matrix multiplications and additions. So a typical neural network looks like this. It's a kind of interconnected nodes where you have this like weights and biases that you are typically, you have some input data, and then you do like a matrix multiplication. So you have a matrix that contains a weight and a matrix that contains some biases. And these essentially make up the values in your neural network that you're going to be doing your operations on. And then after you've like done these operations, you'll get an output layer that tells you the percentage of, say, which categories it fits in. So TensorFlow kind of, so that's how you actually can do prediction with a neural network. So in order to train it, you use a method called backpropagation, which will take some training data that's labeled, that has the correct label, and then putting the data through the neural network and then comparing the data, the output of the neural network, to the expected value that you get. And then you use the training, this back propagation, to take the difference of the expected and the actual output, and then use that to update the weights and biases of your neural network, and then continually train it so that it will get closer and closer to the value that you want or that you expect. So the next thing is, why are we talking about neural networks now? Why is this a really hot topic recently? And I would argue that this is because of a number of breakthroughs in machine learning that have happened recently that basically allow us to get much more useful things done. So this is a neural network that, not typical, but this is a neural network that was developed at Google in order to classify images. So you can imagine that each one of these little boxes is an operation that's done on input data. And this is where the idea of deep learning comes into machine learning or to neural networks. That you have many layers in the network, and this allows you to do much more complicated and useful things. But because there's so many operations, and because each matrix multiplication is many multiplication operations, this is very intensive. This requires a lot of hardware and CPU power. But we can't avoid the CPU or the cost of the doing this. We need to have to, in order to actually do things that are useful. So we have to have these large neural networks where we can give it more data and have it actually continue to learn and get better. With smaller neural networks or shallow neural networks, even if we give it more data, it doesn't learn and get better. It doesn't grow, it doesn't learn, and so we can't continually get better neural networks without having these deep neural networks. So typically what people do is they use GPUs or some type of hardware to accelerate the machine learning, or you use supercomputers. But GPUs can still take hours or days or weeks to train neural networks. And many people don't have access to things like supercomputers that can train your models much faster. So you need a way to kind of distribute training, or to kind of build on, to distribute this among many machines so that you can actually, normal people can do machine learning. And we've been doing this at Google quite a lot. We've incorporated it into a lot of products like Google Photos and Google Street View, Google Maps. And you can see that since 2004, we've had a lot of great breakthroughs, and so the number of projects inside of Google has actually, that are using machine learning, has increased tremendously. So it went from something like maybe 300 down here in 2014 to over 1,500 today. So this is, part of this was how that we built this, this library, TensorFlow. And we did this in order to enable us to do this kind of distributed learning. So TensorFlow is a generic open source library for doing machine learning or machine intelligence. And we open sourced this in 2015, so about 1 year ago. And this is used by many of our machine learning projects inside of Google. So TensorFlow gets its name by the idea of taking tensors and then applying many operations that flow through the neural network in order to get the output. And so that's why we called it TensorFlow. Essentially what it does is allows you to define these operations that you do on the tensors in order to develop these neural networks. And it supports doing distributed training and things like that, as well as using many different types of hardware, like CPUs and GPUs. Some of the core concepts in TensorFlow are graph, which represents the entire neural network or the entire network graph, an operation, which is each individual operation, and then the tensors themselves, the data that's passed through the neural network. And you define the neural network through constants. Constants are basically just data that doesn't change. Placeholders are essentially the input into your neural network. Variables are values that can change as you are training. So these are the things like weights and biases. And then sessions like encapsulate the environment where you are running your training. And TensorFlow supports quite a lot of operations. So you can see here like matrix multiplication and subtraction and addition, as well as many other types of operations. So let's look at an example of what that looks like. Not this one. So this is a tutorial that uses the MNIST training set. This is a fairly well-known training set. Let me clear the output here. So what I'm doing is just basically loading some training data from the MNIST training set. And this MNIST training set is essentially just a bunch of images of numbers that are handwritten. And we want to be able to take the image and then decide what number is written on the image. And so what we're going to do is we're going to take this image and we're going to change it into a tensor. And so each image is, I think, 28 by 28 pixels big. So that means there's 784 pixels. So we're going to create basically an array or a tensor that is 784 values big. So we can see here we have 55,000 values, and each one of those has 784 or 55,000 images, and each one has 784 values. So here's an example of one of the images. So these zeros are all just white pixels, but you can see some of the black pixels. If you scroll down, you can see that some of these have values of how dark the pixel is. And this is, hopefully will run. This is basically just taking that tensor and then just displaying it as an image. So in this case, I have I'm showing a single value from the training set, which is an 8. And so when I take that, I've got the image value, and then I've got a label for each training image. So that says which number is in the image. So this is used to train the neural network. And this is basically just a tensor that is 10, has a size of 10. And in here, it has a 1 in the right spot. So this basically just says that this image here that I had is an 8. So we start from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we know that this one is an 8. And then that is one of the images that I train into my neural network. And then here I have, this is just a representation of how the neural network can see the data. This is a very simple example, but here you can see that these blue areas represent areas where if there's a pixel, then this is positive. This is more likely that it's a 0. And these red areas are the areas where if there's a pixel, that it's more likely that it is not a 0. So this is for 0, and this is for 1, and 2, and 3. So you can kind of see where the blue areas are. It kind of looks like the number that you're representing. And this is, because this is a simple example, you can do this, but this is kind of shows you a little bit about how the neural network thinks. So down here, I can actually define my neural network. So here I'm using a placeholder for the input, and then 2 values for the weights and biases. And these are the values that make up my neural network. And then here, I will do a matrix multiplication on the weights, and then a matrix addition on the biases, in order to build this simple network, or this simple model. So let's do that. And what I get out is I get this object out that I can use to do training. So here, next I can define the training step. So this is taking my neural network or my model of my neural network, and then creating a training step. And this is using a function here to define the difference between the output that's expected and the output that I actually get from the neural network. And then another step for taking that difference that I get, and then applying that to my existing weights and biases in my neural network in order to make it learn and get closer to the value that I want it to get. So these are 2 methods that are typically used in machine learning, called cross entropy. This is to get the difference or the error of the network. And then this one is a gradient descent optimizer, which allows you to take the diff, or the difference, and then train the model so that it gets closer and closer. So here's just a representation of what a gradient descent looks like. So you have some sort of, you start with a high error or a high difference between the expected values, and then you eventually find which direction or how you need to update the model in order to get closer to the value that you want it to be. So this will kind of follow a path, kind of like you're coming down off of a mountain or something like that. So after you've defined this training step, you can then basically run many times over the training. So in this case, I'm just going to run this 1,000 times. So this is still running, apparently. Should take just a few seconds, but. And then after you've actually trained this, you can then use TensorFlow as well to then test your model to see how accurate it is with against the test data, or against your test data. So you can train your model and then apply some of the test data to actually test to see how accurate it is. Looks like the Wi-Fi is not being particularly helpful, but essentially in this particular example, I would train this and then be able to test it and see that the model is about 92% accurate. Yeah, and so that's about that's how you can kind of build a neural network with TensorFlow. So I just wanted to close by saying that TensorFlow also allows you to do this kind of distributed training, and supports several different types of distributed training. And that, in order to kind of make the distributed training easier to do, at Google we're developing things like Cloud ML, which will allow you to run open source TensorFlow graphs using Google hardware. And so this will allow you to build more powerful distributed models that you can use to train. This also allows us to develop things like custom hardware that can allow you to train machine learning models faster. So these are called tensor processing units, but these are essentially just custom hardware that we can build in order to make machine learning faster. So that's all I wanted to talk about, and that's all I really have time for. So thanks for everybody for coming, and hopefully I'm excited to see what you'll do with TensorFlow. Thanks a lot.
Are you going to open source?
Yeah, so if you guys, if you're interested, I think I'll probably, I don't really have time for things like questions and stuff like that, so I'll create an open space later so that you can kind of come by and we can talk about TensorFlow and things like that. So check out the open space board later. Thanks a lot.